All right. So first of all, let me tell you that we are being recorded. I'll be posting the recording as well. However, your attendance will be taken. So make sure you are here in the meeting and not just go by the recording because the recording, posting the recording itself is not an easy task because it's a long recording. So it takes a few hours, maybe even a couple of days or longer. So you want to come here in the meeting so you don't miss things. And let's get started. All right. All right, so I'm going to share my screen in a second. I haven't used Zoom in a while for this kind of college meetings, class meetings where we share the screen and such and open lectures. Perhaps you have classes where you do that, but most of my classes are face to face. So let's see here. Let me get to our material. All right, almost there. And I'm going to share my screen now. All right. Can you see the PowerPoint screen? Okay. So we have basically this is chapter one. We have wrapped up chapter one more or less. We went through everything in very much details concerning the electrons and hold on. No, these are not the PowerPoint slides that we use, right? I just realized that. Let me stop the share and let me get the right PowerPoints. Right, here we are. So this was chapter 1. We studied the electron configuration, quantum mechanics of the quantum numbers, how it all works, the shape of the orbitals, how orbital diagram should be drawn, filling out every orbital, the periodic table and all the different blocks, the S block, the D block, the P block, the F block, bonding, ionic bonding and covalent bonding, electronegativities, polar bonding, spent a considerable amount of time drawing Lewis structures, looking at even odd electron situations and expanded electron situations, expanded octets, I mean. And we looked at this table a lot to understand how bonding will proceed going forward with carbon and oxygen and other atoms that are usually found in organic structures. We talked about resonance. We probably spent about 2 lectures in resonance. A little bit on VSEPR. And then we spent a lot of time on hybridization as well. These were the important aspects of chapter 1. And then a little bit of time on intermolecular forces, the London dispersion, the hydrogen bonding, and the dipole-dipole, right? And I just want to show you one last thing on dipole-dipole, or basically one of these intermolecular forces of attraction. Here we see hydrogen bonding happening, right? Hydrogen bonding, as I have told you, was bonding between a hydrogen that's directly bonded to an oxygen or a nitrogen or a fluorine, because that creates very high polarity. Delta plus is very high on the hydrogen and delta minus is very high on the other atom, the oxygen, the nitrogen, or the fluorine. That hydrogen is going to be very attracted to another oxygen or a nitrogen or a fluorine. Now, the other oxygen doesn't have to be some kind of OH or an NH if it's a nitrogen, or an FH if it's a fluorine. It can be any oxygen with a delta minus on it. As you see here, you got this molecule, which is acetone, the nail polish remover, CH3, C double bond O, CH3. Acetone by itself does not hydrogen bond. If you just have a pure bottle of acetone, and you all have used acetone by now, right? You saw how acetone easily evaporates away. In fact, that's why we use it. One of the reasons. One reason is that it will dissolve things that water will not dissolve. Other is that it will evaporate away quickly. So it's going to drag away anything that water doesn't dissolve and then evaporate away. So we can use it to remove things, and we can count on it to leave the surface of the glassware. Why does it do that? Why does it leave the surface so easily? Because it cannot hydrogen bond within itself. Now, it's a different story if you mix it with water. If you mix it with water, then it will hydrogen bond, and the solution, the mixture will have a higher boiling point because it has mixed with water. Also, because it can hydrogen bond with water, it's going to mix very, very well. It's not like mixing oil with water. Oil and water do not mix, but acetone and water will mix completely. The same thing will happen if you mix alcohol with water, just like the lab on fractional distillation and simple distillation, where you separated a mixture of methanol and water. You could not see 2 separate layers. It was just 1 layer, because they both mix very well into each other. And one of the reasons is because they are both polar, and they can both hydrogen bond with each other. Same with acetone and water here. Right now, to give you the full picture, we learned that hydrogen bonding requires what I just mentioned: hydrogen bonded to an oxygen or a nitrogen or a fluorine. The other kind of bonding, that's between delta plus and delta minus, opposite ends of opposite polar ends of a molecule. Well, that is dipole-dipole, which is weaker. Now, if you just had pure acetone, then this carbon bond, oxygen bond called carbonyl, C-A-R-B-O-N-Y-L, carbonyl bond here, By the way, can you note and let me know if you can see the mouse cursor that I'm moving around on the screen, or is it not visible on your end? You can let me know on in chat as well. That would work. Okay, good. Good. So here, the C double bond O is called carbonyl bond, Carbonyl, carbonyl. So see, this carbon is delta plus and this oxygen is delta minus, even without water being part of this. That is what makes a molecule of acetone somewhat polar, because it can dipole-dipole bond, not hydrogen bond, but dipole-dipole within itself. If there was no water, this other molecule of carbonyl, this oxygen would be attracted to this carbon down here. And then this oxygen would be attracted to another carbon of another carbonyl on an acetone molecule. That attraction will be weaker than what you see right now. That's why it is easy to boil away acetone. That's why the boiling point of acetone is lower than the boiling point of water or the boiling point of the mixture. All right. Finally, the last kind of force of attraction is London dispersion force, which we know is very weak, but it builds up as the surface area of the molecule increases. So here you see very similar molecules. These are all carbon-hydrogen bonds with an oxygen in the middle. First, we start with two carbons with one oxygen in the middle. Then we increase one more carbon, keeping one oxygen somewhere in the middle part, wherever it is. Then we increase it by one more carbon, as you see on the bottom. So here we have two carbons, here we have three carbons, here we have four carbons, here we have five carbons, right? All of this should have the same polarities. They are all dipole-dipole because this carbon-oxygen bond is a polar bond. Oxygen being more electronegative than carbon, as we know from the electronegativity table. The difference is greater than 0.4. Keep all that in mind. We looked at it earlier. So this oxygen is more electronegative than carbon. So this is delta minus on the oxygen, delta plus on the carbon. And it creates a dipole-dipole attraction for another molecule. So dimethyl ether will be attracted to another molecule of dimethyl ether. Similarly, ethyl methyl ether will be attracted to another molecule of ethyl methyl ether. No hydrogen bonding, all right? Because there is not a single oxygen hydrogen or a nitrogen hydrogen or a fluorine hydrogen bond. They are all the hydrogens are bonded to carbon. So there is no hydrogen bonding. There is only dipole-dipole, but I also told you every molecule has London dispersion, whether it's a polar molecule or a non-polar molecule, right? Now we know that dipole-dipole attraction should be the same for all four of these molecules because they have the same kind of bonding between the carbon and the oxygen. Then what exactly is responsible for the rise in the boiling points we see? We go from negative 24 degrees Celsius for dimethyl ether to 7.4 degrees Celsius for ethyl methyl ether, to 34.6 degrees Celsius for diethyl ether, and finally 64 degrees Celsius for ethyl propyl ether. The only way we can explain this is London dispersion forces. Those forces build up as the surface area of the molecule increases, creating small locations between two surfaces of two molecules where they touch each other. And where they touch each other, that's where the attraction happens. Very instantaneous attraction for a very short period of time, but over a large molecule, those attractions, the small attractions build up. That's where you get the that's where you get the London dispersion, force of attraction raising the boiling point. And that's what explains why 50 carbon long chain is basically tar, very black, very gooey material that doesn't allow light to go through it. So it's very black and it's very sticky. And that's why we put it on the road. Here we have three different molecules. Now these three molecules have the same size. 1,4-butanediol. If you count the number of carbons, all three of them have 4 carbons, 10 hydrogens, and 2 oxygens. But they are different structurally. If you notice, they are very, very different. What exactly are they called, by the way? They are called isomers, constitutional isomers. When you have the same formula for a given compound, but different structures, I mean, not for a given compound to be more precise, because there are three different compounds. When there is a one formula, molecular formula, that can represent many different compounds, then those compounds are called constitutional isomers. And the thing is that they all have the same molecular weight because they have the same molecular formula. The molecular weight is 90.12 grams per mole. And they should, in theory, have the same surface area, more or less, unless one is very branched and the other is not branched. We learned last week that if you have a straight chain molecule, it has a large surface area. If you create branching, then it becomes very circular, very spherical, which reduces the surface area. That's not the case here. They're all straight chain, as you see. So they are different molecules of the same size with the same surface area. If the surface area is the same, we expect same London dispersion force of attraction, correct? So what is responsible for these differences in the boiling points? Because boiling points are directly dependent on forces of attraction between molecules. If there is high force of attraction between two molecules, the boiling point goes up. If the force of attraction is low, the boiling point goes down. So here, if you notice, we have this dotted lines to show where forces of attraction, especially hydrogen bonding, takes place. Here is the dotted line 1, then 2, then 3, 4, 5, 6 on 1,4-butane diol. 6 potential hydrogen bonding locations. Then the next one, though, has 5 potential hydrogen bonding location. 1, 2, 3, 4, 5. That's 3-methoxy, 1-propanol. And lastly, this last one doesn't really hydrogen bond because it doesn't have any oxygen hydrogens on it, or OH hydrogens, where a hydrogen is directly bonded to an oxygen. And look at its boiling point, 1,2-methoxy, 1,2-dimethoxyethane, 85 degrees Celsius. Okay, so hydrogen bonding does have a say in this. And in some molecules, it will be hydrogen bonding that will be responsible for the bonding pattern you observe, like in this case. But in this previous case, where there was no hydrogen bonding possibility, there was only dipole-dipole, which was all the same for all molecules, then the only responsible party for this differences in boiling point is London dispersion forces. You need to be able to look at given molecular structures and identify what is the primary source of boiling point as you observe in that molecule. Is it hydrogen bonding? I mean, we are talking about comparing molecules. If you are given a choice of 4 or 5 molecules to compare, you should be able to say whether it's the hydrogen bonding aspect or just dipole-dipole or London dispersion forces that are responsible for the fact that the molecules have different boiling points. Okay. Solubility of molecules also depends on the intermolecular forces of attraction. Now, ions, if you have sodium ion, you have chloride ion, it will easily dissolve, generally speaking, in a polar solvent. A polar solvent that's polar because of either hydrogen bonding, such as water. So if you try to dissolve salt in water or other ionic compounds in water, they will dissolve very easily. Why? Because there are very few exceptions of ionic compounds that do not dissolve in hydrogen bonding solvent. If there is a non-hydrogen bonding solvent with just dipole-dipole bonding possibility, there is still a chance that your ionic compound will dissolve, but it's not so high. Okay? Sodium chloride may not dissolve in acetone, for example, because acetone cannot hydrogen bond. Then lastly, where you just have London dispersion forces, like in oils only have London dispersion. They don't have any hydrogen bonding or dipole-dipole. There you do not expect to see some ionic compound dissolve in it. So you cannot dissolve salt in olive oil, for example. You are at home, most likely right now, can reach into your kitchen, take some olive oil or any oil for that matter in a glass, transparent glass, and try to add salt. You will see that instead of dissolving in salt, all the salt will just go to the bottom and sink. You will see every salt particle at the bottom because Ionic compounds do not dissolve in compounds where there is only induced dipole, because London dispersion force is basically an induced dipole, as electrons crowd in one location, forcing the other adjacent molecule to move its electrons away. That's an induced dipole. Hydrogen bonding compounds will dissolve in other hydrogen bonding compounds. They may or may not dissolve in only dipole-dipole compounds, and the solubility in completely only London dispersion based compounds is very, very low. Those compounds with dipole-dipole attraction have solubility in hydrogen bonding compounds, but it varies depending on the exact nature of the compound. They are very soluble in other dipole-dipole compounds, and they are happen to be soluble in London dispersion force based compounds. Okay. And finally, induced dipole, that's London dispersion based compounds. They are not so soluble in hydrogen bonding compounds, just like the opposite here. And they are soluble in those compounds with dipole-dipole attractions, and they are also soluble in other compounds like themselves, like olive oil is soluble in canola oil, for example. Right? And here are some examples of those solubilities. This symbol means infinity, meaning methanol is completely soluble in water. If you mix 50% methanol and 50% water, all the methanol will be soluble in water. Even if you have 99% methanol and 1% water, that at that point methanol becomes the solvent, but they will completely mix. On the other hand, in this compound here, C6H14, which is a completely non-polar compound, only has London dispersion forces of attraction. There, the solubility doesn't really exist because this is a very hydrogen bonding compound. Now, this compound, while it has hydrogen bond, has somewhat London dispersion as well because of this 2-carbon long chain, right? So that's why it is soluble in this compound, which is called hexane. And as the chain becomes longer, the London dispersion part takes over instead of just hydrogen bonding part. And that's when you can say that because of the London dispersion force of attraction, solubility here is remaining high in C6H14, but it's dropping in water because water is purely hydrogen bonding. As we see here, hydrogen bonding solvent. You have here, we are looking at this situation, this last one, where we have induced dipole. Okay. While there is hydrogen bonding, but as the molecule is becoming longer, the induced dipole part is becoming more prominent. So as that's happening, the solvent, which is hydrogen bonding solvent, which is water, the solubility is dropping. Less and less grams per 100 milliliter. This is how we measure solubility. How many grams of the solute can be dissolved in 100 milliliters of the solvent. So that is why it's moderate to low solubility. While the solubility in induced dipole, another London dispersion based compound, is very, very high. All right. This is something you will come across in biochemistry and also in biology, where you have molecules which have parts which are polar and non-polar. Here we have the polar part called the polar head, also called hydrophilic region, because this polar part interacts with water, water being polar. But the other part here is just a long chain of carbon and hydrogens, which is very non-polar. As we learn carbon-hydrogen bonds, electronegativity-wise, the difference is only 0.4, which is considered non-polar. So if you have this molecule in water, the way the molecules will interact with water is they will all open up, basically, their polar heads towards the water, while they will hide their non-polar tails, as they are called, hydrophobic tails, inside a encapsulated area like this, where they can be away from wall. Okay. This is basically the primary means of your cell membrane. Your cell membrane, that is what you have between different cells. One cell is separated from another cell with a cell membrane, right? That cell membrane is actually made up of this kind of molecules with polar heads and non-polar tails. The non-polar tails are oriented towards the inside of the cell, while the polar heads are oriented towards the outside, where they face blood or any other fluids going through the body. Actually, it's a little bit more complex because it's a dual layer of cell membrane where you have one polar head with a polar tail, and then the inside of the cell is also polar because cytoplasm is a polar liquid. It's a polar mixture of liquids. Cytoplasm is what's found inside the blood. I'm sorry, inside the cell. So that's requires that the side facing the cytoplasm should also be polar. So what you would have is a polar head inside with tail pointing towards this other molecule whose tail is pointing towards it. And so basically the outside of the cell and the inside of the cell are polar with polar hydrophilic heads facing both directions on two different chains, while the cell membrane itself is made up of that hydrophobic chain from the one molecule going out to in, and then starting with the back end of the other molecule, starting with the non-polar tail, going further inside the cell towards the cytoplasm, where you would have the polar head. And if you do not have that dual layer, then this happens with soap. Basically, this is what soap is. This molecule you see here is soap. You might be surprised, but soap is not the scent. I know that all the different kinds of soaps have different scents, but in order to market those soaps, they make the manufacturers add different colors, um, pink, blue, red, orange, you name it, and different scents, and also add antibacterial agents. But the actual component of a soap that removes the dirt is non-polar and water is polar. Or let's say you have oily hands and you want to remove the oil. You don't just go and turn on the tap and put your hand under the water, flowing water. It's not going to work, right? Oil does not flow away with water. But when you put some soap in your hand, you are putting this chemical in your hand. Now, this chemical has this hydrophilic portion, which is going to love water. Hydrophilic means phil means love. Hydro means water. So love for water portion. And hydrophobic, phobia means fear. This part fears or hates water. Well, this part hates water here, but loves the oil. It picks up the oil right in the center here. They all line up this way, and inside here would be the oil molecule. The rest of the molecule, the hydrophilic part of the molecule, loves water. So as the water is flowing from the tap, it drags this molecule with it, the soap molecule, because of the hydrophilic portion of the molecule. But the hydrophobic portion of the molecule is attached to the hydrophilic, and the hydrophobic drags the oil particles with it. And that's how you clean your hands of the oil whenever you wash your hands if they're oily. All right, so that is it with what was remaining in this chapter. Let's get into the next chapter, chapter number 2. Let me stop the share here. Here is chapter 2. As I had said, this chapter is on acids and bases. This chapter is considerably smaller, shorter, because there are only few simple facts concerning acid behavior and base behavior that we are going to investigate. This is sort of like what you learned in General Chem 2, just like chapter 1, which was General Chem 1 with extension of some topics, looking at things more deeply. Here, you are going to look at Bronsted acids and Bronsted bases. and as well as another definition known as Lewis acids, Lewis bases. But unlike General Chem 2, where you did a lot of math, complex math with quadratic equations, if you remember, whenever you took 1412 or General Chem 2, as it's called. In this class, in this chapter, you are not going to need the calculator at all. All right. So let's get into it. First, let's define what's Bronsted-Lowry acid and basis. And later we'll define the Lewis acid basis. Then we will look at the equilibrium, the acid-base equilibrium. The main idea in this chapter is which side the equilibrium will lie. Will it lie towards the reactant side or will it lie towards the product side? Now, we are not going to simply be looking at quantitative data to be able to figure that out, although that's where we will start initially. But then just the nature of the structure of the acid and the base, that should allow us to also have some clue where the equilibrium lies. So we will look at different factors in the structure of the molecules which govern the strength of the acid, as well as if it's a basic compound, then the strength of the base. Let's start with simple thing here. We have this reaction, okay? Now you learn that an acid is a compound that releases a proton. That definition was known as the Arrhenius definition. An acid is a compound that releases H+. And similarly, Arrhenius, a chemist from the 1800s, early 1800s, gave another definition for a base. A base is a compound that releases OH-. So H+ is released by an acid and OH- is released by a base. Now that definition worked for a while. Science was just developing in the early 1800s, but that definition limited the number of acids to a handful, just about 10 or so compounds which could release H+. But the real severe limitation was on the number of bases. We had about 8 bases which could release OH-. Compounds like sodium hydroxide, potassium hydroxide, barium hydroxide, calcium hydroxide, strontium hydroxide, magnesium hydroxide, those compounds, they could release OH-. But that definition could not explain all observations. There were compounds out there which would turn the water alkaline or acidic, even if OH- was not released or there was no OH- present. So in the early 1900s, two scientists, Bronsted and Lowry, they both got together to give a new definition to an acid and a new definition to a base. The definition of the acid is more or less the same as the other definition, the 100-year-older definition from the 1800s. The new definition, though, was that an acid is a compound that donates a proton. So the key word here is donate. Arrhenius said that H+ is released. Bronsted-Lowry said that H+ is donated. Okay, keep that in mind. Donated means it's given to somebody in the solution. Release means it's just out there lying around, flowing around, floating around in the solution. Is H+ simply floating around? Not really. H+ gets picked up by water. What happens is you have H+ that is released in the solution, and that H+ actually gets picked up by water, H2O. And what comes out of it? Can you tell me? You know this from General Chem 2. It is H. Three.
Oh,
Yeah, I got one.
H.
Yeah, that's right, Joseph. H3O plus. Yeah. What is it called, by the way? As an M. It's called hydronium. Hydronium ion. Hydronium. Hydronium. Right? So you know this already from General Chem. Whenever you did those complex equilibria problems, right? What are the ice initial change and equilibrium, right? All those things you did. You were showing that the other side of the equation, when an acid was reacting, the other side was basically the side with H3O plus, right? So that's what it is. Uh, okay. And what was the definition, the new definition of a base that Bronsted-Lowry gave? The Bronsted-Lowry definition of a base is extremely or very different from the original Arrhenius definition. Arrhenius definition required the presence of OH minus to be there in the original molecule, like NaOH, sodium hydroxide, KOH, potassium hydroxide. But the new definition simply said that a Bronsted-Lowry base is a compound, a base that accepts a proton, accepts an H plus. So just right, few minutes ago, where before I erased my screen, I showed you how H2O, water, is accepting that H plus. What does that make water? According to the definition by Bronsted-Lowry, water is acting as a base. No way would that be the definition of a base by Arrhenius. Arrhenius would never classify water as a base. But if in a given situation, if water accepts an H plus, it's acting as a base. Now, because of this situation of a compound accepting a proton being called a base, very novel situations, novel conditions could result in solutions where in one solution, a compound is accepting a proton like water, and that's why it's called a base. In another compound, in another solution, water is releasing an H plus, acting as an acid. So compounds could act as an acid or a base, some of them at least. Let's look at this example here. You have CH3COOH. CH3COOH, whenever you see COOH in organic chemistry, please realize that it's called an acid. COOH is the definition of organic acid. This is called a functional group called carboxylic acid functional group. Carbo, C-A-R-B-O. Xylic means X-Y-L-I-C, carboxylic acid. Okay. And carboxylic acids are what basically you taste whenever you drink any fruit juice or any vegetable that has any acidity to it. It's all coming from the organic acids. This part, the CH3 part, would be different. If you eat an apple, apple has something I believe called malic acid. But if you eat an orange, orange has citric acid. Well, both of those acids have COOH, but this part is different here. Okay. So what is this acid exactly? This is the acid found in vinegar. This is called acetic acid. If you take vinegar, which is a mixture of water and acetic acid, and evaporate away all the water, then what's left behind is acetic acid. If you take acetic acid and mix with some compound, any compound like sodium hydroxide, potassium hydroxide, one of the traditional bases, or what will happen? The acid will donate a proton, and the OH part of the other molecule will accept that proton. Okay. So the OH part of potassium hydroxide, for example, will accept that H plus, and OH minus plus H plus gives you H2O. While what happens to CH3COOH? After it donates away the CH plus, what's left is CH3COO minus. Now, I know you studied all this, but I want to ask you to pay attention to the signs, the negative signs and positive signs if they are there. Remember, H plus is the one that gets donated. H plus is just a proton without any electron. A hydrogen atom has a proton and an electron. But what gets released away and donated is just the H plus. So there is an electron that's left over with the original molecule. So there is an excess of one electron. That is why the sign on this part here is CH3COO 1 minus, or simply minus. Here we had OH minus, hydroxide. There was an excess electron and it picked up one proton. So now there is no excess of an electron. That's why on this side here, it's simply H2O. Okay, two hydrogens now, because there was already one hydrogen and the H plus. There was this hydrogen and the H plus together making H2, and the oxygen was already there. So what results in a Bronsted-Lowry acid-base reaction? In a Bronsted-Lowry acid-base reaction, on the right side of the equation, you will also have an acid and a base, because simply an acid is a compound that donates an H plus and a base is a compound that accepts an H plus. So if you look from the right to the left, look from this side on the right, go to the left. What is happening? Let's start with this compound, H2O. From the right, H2O, if it goes to the left, because there is a double arrow, an equilibrium arrow, meaning what? That this is an equilibrium process. For those who forgot, equilibrium processes are processes which do not go completely to completion. They do not start with the reactants and end with only the products. Instead, you start with the reactants like this too. It goes towards the products, converting the reactants to the products, but it does not go to completion. At the end, when the reaction is over and you come to check, you will have substantial amount of the products, but also substantial amount of the reactants left over. You are in a state where the reaction is not going anymore. What exactly is happening? Again, this is just a review of the equilibrium process. What is happening? That the products are converting back to reactants while the reactants are converting to products, and that both is happening at the same rate. Initially, only the reactants were turning into products. But as the amount of products went up, the products are also converting back to reactants, and both the conversions in each direction is happening at the same rate. Meaning that within a given moment, if one molecule of the reactant is forming from the products, then in the same moment, one molecule of the reactants are converting to the product. So it's like saying that initially I was walking only forward, taking 10 steps forward. But by the time I took my 10 steps, then I was required to take one step back, right? Then I continued moving 10 steps forward, one step back, and so on. But then I started taking 2 steps back, 10 steps forward, 2 steps back. So a little bit of going back. But then eventually I reached a point where I was going 10 steps forward and 10 steps back, 10 steps forward, 10 steps back. At that point, I'm not moving anywhere. I'm remaining where I am, because as soon as I move 10 steps forward, then I move 10 steps back, meaning I go from reactants to products and back from products to reactants. This happens constantly. That's the equilibrium process you see here. So at equilibrium, when the reaction is basically over, no change is happening, you would see all the 4 present in the solution, right? And if you notice water here on the right side, what is happening as it goes back? It's turning into OH minus. To turn into OH minus, it has to lose an H plus or donate away an H plus. But that's the definition of an acid, right? According to Bronsted-Lowry, a substance that can donate an H plus is an acid. So water is acting as an acid from right to left, while from left to right, CH3COOH was acting as an acid. How do you differentiate the two acids? The one on the right is always called a conjugate acid. Okay, conjugate, like conjoined. Conjoined twins are joined together in some way. That's where conjugate comes from, that this molecule is joined with some other molecule. Which exactly? Conjugate acid is not joined with the other acid. Conjugate acid is connected to the base on the other side. So they both originate from the same source. That's the idea. The base and the conjugate acid. Similarly, the acid here and the conjugate base. This molecule CH3COO minus is converting into CH3COOH by accepting an H plus. Acceptance of an H plus makes it the acid. All right, so you have the acid and the conjugate base, and the base and the conjugate acid. You should be able to identify the pair all the time. let me ask you this question here. I have this molecule OH, or rather an ion OH minus. We write down the acid first and then the base. So if this is my acid, original acid, what is going to be the conjugate base on this side? Please tell me. And then here, I'm going to write down for another molecule. You can answer me on chat, and you can answer to me as a direct message so others don't see it. So H3O plus is my conjugate base. What exactly is the acid here? And similarly for OH minus, which is my acid, what is the conjugate base? Okay, I got a few answers. Let's see. Can you hear me? Seems like my screen is frozen here. Okay.
No, we can hear you.
Okay. The chat box is frozen on the screen. It's not
Oh,
moving.
so somebody is saying that H2O.
Yeah. So, okay. Can you write your answers again for just the first molecule, the one up here? This one. Then we will look at this one. I'm unable to scroll to look at your answers. So, what is the conjugate base here for OH minus? That is incorrect, Seth. Remember, what is a conjugate base? A conjugate base is the compound that forms when the acid donates away an H plus. Sarina, that is correct. The answer is Sarina, that's almost correct. It would be, well, no, you are right. You're right. I see why you, yeah, okay. It's O2 minus. I initially thought you meant the 2 down here, but no, that's unfortunately on chat box, you cannot write it clearly like that. You cannot show the subscript and superscripts. But yes, this is the answer. Why is this the answer? O2 minus. When H plus is gone, there is an excess of one more electron. There was already a minus charge. Now there will be another minus charge. So there was one minus. Now there will be two minus. O2 minus. Okay. Now what about here? What is the acid whose conjugate base is H3O plus? Yes. Now I know that that is correct, Hannah. There is no such thing as what the answer is, but applying the rules, this should be H4O2 plus. Now there is no molecular species like that. I will be honest. But if there was one, then a loss of a proton with a plus charge means that 2 plus becomes 1 plus and H4 becomes H3. Okay, this is what the answer would be. So the idea here was to see whether you can come up with the conjugate acid or the conjugate base or the one or the other of the pair. Okay, that's how it works. Now, let me try to see if I can clear the screen. I think I know why I was unable to earlier move up the chat box because I had to close my, yeah, now it works. I had to close the annotations. That's why. Okay. All right. So moving forward, here is a reaction, another reaction. CH3 C double bond OOH. Well, the same reaction actually. How it happens. Now we are showing the arrows which we learned how to show in organic chemistry. We learned the arrows with resonance, right? These are not your resonance arrows. These are your actual chemical reaction arrows. It's important to learn these arrows as well. The arrow always starts from a pair of electrons. That pair of electrons is goes to the atom, ending towards the atom with the arrowhead that gets picked up. Okay. So this is the acid molecule CH3 C double bond O OH, the Lewis structure of it. And your sodium hydroxide. The sodium is just a spectator, doesn't do anything. It's the hydroxide part that's the base. This pair of electrons grab this proton because this proton gets donated away to it. And when it gets it, there is this bond here. Now this is a reaction. So now what notice, unlike resonance where you could only do this with a double bond, moving one of the two bonds of a double bond to one of the atoms, here you are actually breaking this bond. And that means it's a chemical reaction. And so these electrons, two electrons move towards this oxygen, which become these electrons here with a negative charge, right? And this becomes H2O, as you see here. Now going from the right to the left, the conjugate base, this pair grabs this proton, one of these two is shown here that it grabs this one, and this pair of electrons move towards this oxygen, forming OH minus and forming the acetic acid. Now the equilibrium, K equilibrium has a formula. Okay, you learn this in general chem, but to remind you, K equilibrium is the forward rate of the reaction divided by the reverse rate. The forward rate constant divided by the reverse rate constant. K1, that's the forward rate constant. Rate constant is how fast the reaction is moving in one direction. That K1 is the forward direction, and K1 minus is the reverse direction. The ratio of these two gives you the value of K equilibrium, uppercase K, okay, equilibrium constant K. Now, K could be a very large value, large as in 1,000,000 or 10 million, or it could be a small value. Value of K could only be one of the three conditions. K will be always greater than 0, always, but less than 1. That's one possibility. K equilibrium is what we are talking about. Sometimes we don't write EQ. It could be exactly equal to 1. And the last possibility is K is basically greater than 1. Okay. All these three conditions tell you about the equilibrium. If K is between 0 and 1, then the equilibrium lies in which direction? Forward direction, reverse direction, or are they both equal? Meaning the concentration of the reactants is equal to the concentration of the products. So again, you have three choices. If K is between 0 and 1, do you have high concentration of the products, which is the forward direction, or high concentration of the reactants, which is the reverse direction, or both the concentrations are equal? What is your choice? That is incorrect, Hannah. If K is between 0 and 1, then the equilibrium lies in the reverse direction, meaning that you have high concentration of the reactants and low concentration of the products. Notice how it's a forward rate divided by reverse rate, right? The value of the reverse rate has to be very large in order for this expression, like let's say K1 was equal to 1, K negative 1 has to be larger than K1, let's say 50. So 1 divided by 50. That's when you get a value between 0 and 1, meaning the reverse rate has to be higher than the forward rate. All right. So when you have high concentration of these reactants at equilibrium, when everything is over and nothing is changing, that's when if the K value that is found to be between 0 and 1, that tells you that you have high reactant concentrations, which means the product concentrations will be very low. That means the reaction barely went forward. It went forward a little bit. You got a little bit of products, but mostly it stays in the form of reactants. It doesn't really want to go forward. And at equilibrium, you have high concentration of this, if this was the condition here. Now, if K is equal to 1, that means K1, the small K1, the rate constant K1 and the reverse rate constant K1, K negative 1, both are equal to each other, right? If they are both equal, that means the forward rate and the reverse rate constants are equal. And when that happens, that means that you have the same concentration of the reactants and the products. So 50% of your mixture is made up of the original reactants and the other 50% is made up of the products. That's what it means. And lastly, if the value of K is larger than 1, that means the numerator here, K1, would be larger than K negative 1. That means that at equilibrium, you have high concentration of the products and low concentrations of the reactants, all right? Any questions about this? Okay, no questions. Now, that's the acid-base definition according to Bronsted-Lowry. Here is the Lewis acid-Lewis base definition. Gilbert Lewis was another chemist who was very influential in organic chemistry. And that's, in fact, he's the one from whom you get the Lewis structures. So he was one of the pioneers in developing organic chemistry as well. And in organic chemistry, you might be surprised, but 90% of all chemical reactions in organic chemistry are classified as acid-base reactions. All right, everything you will study in this course going forward, most of it will be classified as acid-base reactions. But the definition of the acid and the base is different from Bronsted-Lowry. We call it the Lewis acid-Lewis base definition. So here is the Lewis acid definition. Lewis acid definition is a substance that accepts a pair of electrons. Now, that's a weird definition, I agree, but it works because ultimately the solutions you get are going to be acidic if you have a Lewis acid. And if you have a Lewis base, you will get an alkaline solution. A Lewis base is a substance that donates a pair of electrons. Let's see this in action. And then we will see how is this different from the Bronsted acid base. Here is your Lewis acid base, the reaction you see here. Now, you got boron trifluoride, also known as trifluoroborane, and you got water. When they come together, they simply form a chemical bond. The boron atom here lacks an octet, and it accepts a pair of electrons from water. So if it is accepting a pair of electrons, then it is a Lewis acid. And water is donating that pair of electrons to the boron atom, shown with the arrow this way, starting from the Lewis base, going towards the Lewis acid. You will always see the electron, the arrow, always start at the electron pair, and the electron pair will be on the Lewis base, and it will go to the atom, that's the Lewis acid on the molecule, the other molecule. And that's where you get this product. Now, here is the difference between Lewis acid-base definition and Bronsted acid-base definition. The Bronsted acid-base definition earlier here always had a conjugate acid and a conjugate base. That is always going to be the case. There will be a conjugate acid and a conjugate base, which you can link up to the acid and the base on the other side. However, with Lewis acid and Lewis base, there is no such thing as having a conjugate acid and a conjugate base. You may have something similar, but you may not have something similar. In this example, you don't have any similarity. You just form a bond. That's it. And that is, you cannot look at this molecule on the right and call it either conjugate acid or a conjugate base, because there is no such thing here. Then we got another example on the bottom, thiolate, a very extremely intensely smelly chemical because of sulfur, and bromomethane. Now, what is happening here? This is also a Lewis acid, Lewis base reaction. If you notice, this one of the 3 electron pairs on the sulfur atom ends up forming a bond with this carbon. This bond that's formed is not formed by carbon coming up with 1 electron and sulfur coming up with the other electron. It's not like that. Both the electrons come from the sulfur, right? Just like both the electrons up here came from the oxygen. So a pair of electrons are being donated by thiolate. And that makes thiolate your Lewis base. And that makes this compound acceptor of that pair of electrons. So it's called the Lewis acid. And here is the outcome. And now the outcome is that bromide has to leave. Bromide does leave here. Bromide cannot remain bonded to the carbon, because if it was remaining bonded, you would have 5 bonds around the carbon. A situation with 10 electrons, that's not allowed for carbon, right? Carbon cannot have expanded octets. So all of this is happening, but ultimately this is your Lewis base, this is your Lewis acid. These are the products of the reaction. Now, this is also an equilibrium process, and the reaction goes in the reverse direction back to the reactants, where bromide will act as a Lewis base, forming a bond with the carbon here as you go from this compound here to forming bromomethane. And because this molecule is accepting that pair of electrons from bromide, it makes it the Lewis acid. In this case, in this second example, you have a situation that's similar to Bronsted acid, Bronsted base, where you have the conjugate acid and the conjugate base. But notice that it's not that similar because bromide is acting as a base here, but it doesn't really have any much say here. It's just leaving here. So unlike the Bronsted acid and its conjugate base pair, there is no such pairing that's happening here. Okay. Here you define everything by who is accepting a pair of electrons and who is donating that pair of electrons on each side. Sometimes on both sides you could see that, sometimes not on both sides, like in this first example. And I will let you know right now that almost 90% of your chemical reactions that you will be investigating in this course will be of this kind, Lewis acid, Lewis base reactions. They have a special term for that, and I will let you know right now that the term for this is how do you, when I was asked a question on chat, how do you know which one leaves? Yes, that is a very good question. How did I know that bromide left? But the reason that bromide left is because it's considered a good leaving group. However, you will know why it leaves in chapter number 6. It's way down the line. It's not anywhere near. We are not anywhere near to investigating the reason why it's leaving. But I will just let you know, carbon-hydrogen bonds do not break easily. Okay, but carbon-halogen bonds do break relatively easily. That's all you need to know now. And you will not be asked to name the atom which will be the leaving one, the one that leaves. That is something you will learn about much later. And by then you will understand why it leaves. So as I was saying earlier, the Lewis base is given a name. It's called a nucleophile. The name Lewis base is not something that we commonly call it by. We call it a nucleophile. NuClEO. I know my writing looks very bad. This, by the way, is NuC, nucleophile, PHILE. You know, like hydrophilic or hydrophile. This is nucleophile, PHILE. Why is it called a nucleophile? A nucleus is just protons and neutrons, right? So a nucleus is positively charged. To call something a nucleophile means that it has attraction for a positive charge or some kind of delta plus. So in this molecule of bromomethane, bromide has a high electronegativity compared to carbon. So this bond is polar bond. There is delta plus on the carbon, delta minus on the bromine. And the delta plus is what attracts this negative charge. That's why thiolate is the nucleophile. Now, the name for the Lewis acid, which we also don't call it Lewis acid commonly, the name is electrophile because it pulls electrons towards itself. EL E C T R O P H I L E. Electrophile. Okay. Those are the terms you will be calling them by going in as we study future chapters. Nucleophile and electrophile. Here also, between these two compounds, this one, the one from which the arrow starts, the one that's donating a pair of electrons, the Lewis base, is your nucleophile. And this compound here, the Lewis acid, is your electrophile. Okay. All right, erasing my writings. And how much time we have left? We have a few minutes left. So let's just review a few things from General Chem 2 as we investigate whether the reaction lies in the reverse direction or the forward direction. We will be doing that investigating on Wednesday. But here, remember a few things from General Chem, that the acid and the base, the H3O plus, the hydronium, that's the acid part, and the OH minus, the hydroxide, that's the base part. Now, acid-base chemistry only happens in aqueous solutions, okay? Aqueous, we are talking about Bronsted acid-base conditions. Lewis acid-base conditions do not require the solution to be aqueous solution. You see, there is no water present here. But whenever water is present, H3O plus will be the acid that's left over after the reaction, and OH minus is what will happen to the other part of the molecule. That's why we have Kw, the water self-ionization constant, H3O plus times the OH minus. That's 1 times 10 to the negative 14 at 25 degrees Celsius. Now, when the concentrations are equal, we say the solution is neutral and the pH is 7. pH is the negative log of H3O plus concentration. Acidic solution have H3O plus concentration higher than OH minus concentration. The product of both of them will still be 1 times 10 to the negative 14, but H3O plus will be higher than OH minus. That's an acidic solution. And when you take the negative log of H3O plus concentration, the value will be anywhere between 0 and 7. And that's what makes it acidic solution. It can actually be less than 0, but those are the very acidic solutions. Like pure HCl or pure sulfuric acid and such. Basic solution is when the H3O plus concentration is less than OH minus concentration. It's going to be less than 1 times 10 to the negative 7. And then when you take the negative log of H3O plus, that's when it will come between 7 and 14. Again, it can be higher than 14 for very basic solutions, but generally speaking, it's going to be between 7 and 14. Right? You do not, in this class, you do not need to look at all the details you are seeing here, down here, such as the Henderson-Hasselbalch equation, pH equals pK plus log of base over acid, or the POH version of it. You do not need to go into all that. This is just for review. But just I want you to be aware of this last one, that whenever you have a pKa of a given acid, if you take the pKb of the conjugate base of that compound, so if my acid was H3O plus and the conjugate base was H2O, or if my acid was OH minus and the conjugate base was O2 minus, like the example I gave you earlier, the pKa plus the pKb will equal to 14. This last thing will become important as we investigate which side the equilibrium lies on Wednesday. As an example of what is going to come, let's just look at this and then we are done. Look at this reaction. You got this acid. We don't need to know the name of it. It's actually acetic acid, but just look at the structure. And we got this sodium hydroxide. Earlier, we saw this reaction, as a matter of fact, as an example of Bronsted acid-base reaction. Now, there is one more addition in this reaction. It's the pKa values. pKa is 4.75 here. Remember, pKa applies to acids. The A is the acid. As I showed you earlier in the previous slide here, pKa has to do with the acidity. pKb has to do with the basicity. Okay, the pK applies to the acid and the pKb to the conjugate base. So in this example here, this being an acid which donates a H plus has a pKa of 4.75. On the other side though, water is acting as an acid by donating this H plus to this molecule. Its pKb, it also has a pKa and it's 15.7. Now, which is a stronger acid? Stronger acid will always have the smaller of the two pKa's. Okay. If I have a pKa of 1 and a pKa of 2, pKa of 1 is smaller than 2, and then whichever compound had pKa of 1 is a stronger acid than the other compound which had a pKa of 2. So here, between acetic acid and water, the conjugate acid on the other side, which is the stronger acid? You tell me on chat. Acetic acid or water? Nobody? That is correct, Hannah. Acetic acid is the stronger acid because the pKa value, the smaller it is, the stronger the acid. Okay, just like how pH, the smaller the pH value, the stronger the acid. pH 1 is a stronger acid than pH 2. The pKa has the same formula, negative log of Ka. So the larger the value of Ka, the smaller will be the value of pKa. So the smaller the pKa, the stronger the acid. Now, here is the important part. Whenever an equilibrium happens like this situation, the equilibrium will always lie in the direction of the weaker acid. All right, meaning that when you start with just the reactants, when the reaction is over and there is equilibrium established where no change is taking place anymore, then the concentration of the products here will be higher than the concentration of the reactants because the weaker acid is on the product side. If the weaker acid had been on the reactant side, then the equilibrium will lie to the weaker side, which would be on the left. But you see here the arrows have been modified this time. They are not the same size. The forward pointing arrow is longer than the reverse pointing arrow, which is to indicate that the equilibrium is lying to the forward direction, in the forward direction. All right. Now, here is another question. If this is my acid, the conjugate base for this acid is the one of these two compounds. It should be clear that it is this compound, right? This one is called acetate, sodium acetate. What is the pKb of this sodium acetate? That's the last thing I want to ask. Give me your answer on chat when we end this. What is the pKb of this compound? That is correct. 9.25. The pKb of that compound. Why is it 9.25? Because we just talked about the formula earlier that pKa plus the pKb of the conjugate base should equal to 14.0. So if the pKa is 4.75 and if 4.75 plus x equals 14, then x will be 14 minus 4.75. And what about this compound here? This is the pKa of water. This is its conjugate base or its base. So this compound has a pKb. What is the pKb of hydroxide? Anybody? Negative 1.7. That is correct. That is correct, Serena. That is correct, Hannah. Because 15.7 plus x must equal to 14. Right? So x must equal to 14 minus 15.7. That's negative 1.7. Now, if you look at these numbers, you will realize that while we just compared the pKa's of the two acids, and I said that whichever is the weaker acid, meaning whichever has the larger pKa, that's the weaker acid, that's where the equilibrium lies. But if you did not have the pKa's and if you just had the pKb's, you will also notice the same thing. Here is a pKb of negative 1.7 and here is a pKb of 9.2. Whichever is the larger pKb is the weaker base. Just like a larger pKa makes a weaker acid, a larger pKb makes a weaker base. And so if I just looked at the pKb values, this compound here is the weaker base than this compound, and the equilibrium will lie towards the side of the weaker base, which means the weaker acid and the weaker base go together. If you find out that you have a weak acid of the two acids, the compound it is paired up with on that side will also be the weaker of the two. It will be the weaker base. All right. Now we will do more examples of this on Wednesday when we meet. And that's all for now. I want to say this, that Wednesday, we will meet for lecture online because our room is getting painted. We cannot be there. And then we will also continue our discussion for the lab online. But then we will meet at college for the lab. And I'm going to give you 45 minutes. Is that enough to be at college? Some of you might already be at college, honestly, I know, because you might have classes or not, but it might not be very far away. But I'm assuming some could be living very far. So right after we are done with our online meeting for the lecture portion and the pre-lab discussion, we can meet at college for the actual lab, and it will eat away at 45 minutes of our time. So I'm going to have to shorten that lab a little bit. And it's 2-part lab, but we can do just 1 part and be happy with it, depending on whether we can, whether we need the extra time or not. It's otherwise not a very long lab, but there is a chance that it can get longer. The recrystallization part, recrystallization through water, and then recrystallization through ethanol. We might just do recrystallization through water and that's it. But we will talk about it on Wednesday. So we will meet online on the same link, and then we will also talk about the lab. Or the better idea, how about this? we finish our lecture and then we do not have pre-lab discussion. We simply meet in the lab at our usual time because we spend about 45 minutes in the lab. In our classroom discussing the lab. Instead, I could give you that time to travel to the college and meet at college. So we have full time to actually do the lab. My assumption would be that you would watch the video for the lab that is posted and come prepared. And a few small things that are particularly applicable to our lab, I will discuss all those things in 5 to 10 minutes as we start the lab. That I think is a better way of doing this, though, so we don't lose the time. Do you all agree? You can let
Yes.
me know in chat. Okay.
Yes, we don't mind.
Okay. So then we will finish our lecture around 10:40, and then we will meet 45 minutes later or so. Let's just say 11:30. 11:30 is when we meet in the actual lab room, room 104. Okay. Yeah, if you are off by a few minutes, that's fine. If you are late by a few minutes, I'm not going to hold it against you. All right. All right, then this video will be posted soon on YouTube, and it might take a day when it all gets ready because it takes time to process, but it will be online. All right. And I will see you on Wednesday.
Have a great day, Professor.